So welcome back to Multigrid Methods. We're in chapter 4. We started chapter 4 last time where we were discussing the beginnings or the key components that we need to do a different type of analysis for the convergence of our two-grid method. And in particular, we're going to use this more modern energy norm analysis approach, which requires two features. An approximation property and a smoothing property. So I'll get into what that means. But basically, approximation property, that means some error tracking of how well the coarse grid correction performs or what the coarse grid correction does. And then another error analysis of what happens during smoothing. So there are basically two key components of a two-grid algorithm. There's the smoothing, and in the one-sided, in the simplest version of the two-grid method, we only do pre-smoothing and we don't do any post-smoothing. So there's that smoothing step that we do, and usually we're going to use, to keep things simple, a Richardson type of method, or equivalently some sort of weighted Jacobi method. So that's the smoothing part, and the approximation part is the error analysis that we do for the coarse grid Ritz projection. And so those are the two components that we're going to join together. So let's take care of the approximation property first. So this means that we have to quantify the error associated with doing the coarse grid Ritz projection. So we went through this stuff last time. I won't go through this again. Just some basic things that we need to recall about the stiffness matrix, the eigenvalues, a couple of new norms that we introduce. And the thing we want to prove first is this lemma, and it says that the error in the coarse grid Ritz projection, so that's this error here, times any, so that's a matrix, times any vector v1, which is arbitrary, measured in the one norm. So this means the Euclidean norm on level 1. So this is the fine grid Euclidean norm, is equal to a constant, which I'll come back to in a moment, times the norm of the same vector. So notice that these are the same in both locations. The only thing that's changing here is we're changing from the Euclidean norm to this energy norm. So remember, anytime I write something like that, I mean energy norm. And of course, as you recall, so if I want to take the Euclidean norm of a vector, that's just the square root of the Euclidean inner product of that vector with itself. And if I want the energy norm, so it's Euclidean norm, but remember we decided we're not going to use a 2, we're going to use a 1 to indicate that that's the Euclidean norm on the fine level. And if we want the energy norm, that's the so-called A1 norm, then we need to take the square root of the A1 inner product of the vector with itself. And the A1 inner product is most commonly written in terms of the Euclidean inner product by its formula. So it's just going to be A1, V1, V1 in the one inner product. Okay, so those are the objects that we're using or that are involved in this calculation. So what we're saying is that whenever I measure the error in this energy norm, okay, and measure the error in the energy norm, so Euclidean norm versus energy norm, then the difference between those is a simple constant factor, and it involves some very familiar things. So it involves square root of 2, and then 2 is divided by this thing we're calling capital lambda 1. Capital lambda 1 is the number 4 over h1, and this guy serves as effectively, it's like a spectral radius for the eigenvalues for our stiffness matrix, or in other words, an upper bound. So if you recall, we showed that these eigenvalues are all positive and they're all bounded above by a number. And the number that they're bounded above by was exactly 4 over h1. Okay, so that's a bound which is independent of h1, or sorry, independent, actually it's not independent of h1, but it's asymptotically sharp, I should say. But it's independent of k. So this holds true for all k between 1 and n1. All right, so that's where all of these components are coming from. This is the Euclidean norm of this error matrix for the coarse grid Ritz projection, and the norm of the same vector but measured in the energy norm, and they're related through this very curious number, which works out to be related to this upper bound of our eigenvalues. All right, so let's get into this estimate and why, and then later on we'll address why it's useful. So to prove it, what we do is we're going to expand the basis, or expand V1 in a basis of eigenvectors of A1. So that's a fairly standard expansion. The coefficients that we'll use in this case are V1K. Now we're also going to recall a theorem that actually was like a proposition. We showed how these, or this coarse grid Ritz projection error maps vectors that are either higher frequency or low frequency. All right, so I took Calvin's advice and I put like a warning label on here. So this one's low frequency because these vectors are for k between 1 and n0 plus 1. And these are high frequency vectors because k prime is derived from k that is in the low frequency range. So remember how things go. So just as a way of, suppose n1 is equal to 7, and we have k and k prime. So k is the wave number, k prime is the reciprocal wave number. So we count 1, 2, 3, 4, 5, 6, 7, and then we're done. And then k prime, that's defined as n1 plus 1 minus k. So that one runs from 7, 6, 5, 4, 3, 2, and 1. And right here at the middle, that's n0 plus 1. That's kind of the halfway point. So we agreed that these vectors here were all high frequency. And we kind of, 4 sits on the fence. You can kind of label it as high frequency, low frequency. I think just to choose, we decided to make this one high frequency. And then these vectors are low frequency. So if I count k in the low frequency range, and I bump up and grab this n0 plus 1, then the vectors that I get for k prime are going to be the high frequency relatives. And of course, there's something weird going on here with 4 because it's kind of both high frequency and low frequency. So that's how I'm doing the counting here. K for k between 1 and n0 plus 1, and k prime for k between 1 and 0 plus 1. So this is how it maps these vectors. It maps them to themselves times this trigonometric. So this was sine squared k pi h1 over 2. And ck was cosine squared k pi h1 over 2. Those you can check if you plot those guys. One goes like this. I think it's the sine. And the cosine goes like this. They actually agree in the middle right here. And I'm plotting this along k, and so this is n0 plus 1. They agree right in the middle. And that's why if you look back, whenever we proved this for the first time, this one of these two labels didn't go all the way up to n0 plus 1. I think it's this guy. But I can extend it by 1, and the reason is because when I extend it by 1, I'm going into this territory, but this SK and the CK match. All right, so I'm not really doing anything. I'm not cheating or fibbing when I index this by 1 extra. Now, so how do I view this? So this says if K is a low frequency vector, if K is a low frequency vector, then what we expect is that the error for this low frequency vector should be basically 0, should be small. Right? So that actually pans out. If K is equal to 1, if K is equal to 1, then this SK is very close to 0, and this 1 mode, this very low frequency mode, gets returned to another low frequency mode. All right? But with a 0 or something which is a coefficient which is very close to being 0. But it also returns something which is small and in the high frequency range. In fact, if this is K equals 1, then this is the highest possible frequency, right? So K equals 1 corresponds to K prime being the highest frequency. So I still make a small error, all right, in this one, and it adds a new mode, which is in the high frequency range. So this is kind of how you can divide these things up and think about how this, this coarse grid error is working. Now the error should be smallest for the lowest frequency range, and it should be highest when you go or we transgress into the high frequency range, because the coarse grid doesn't do a very good job of keeping track of high frequency information. So for example, whenever K is equal to 1, K prime is equal to 7. So let's measure the error there. All right? So this error should be relatively large because this is now a high frequency component, right? So let's see what we get. We get a low frequency vector multiplied by a CK, but CK, K is very small, it's close to 1, so that's pretty large. So it's returning a large vector or large error associated with the lowest frequency mode, and it's returning a large error associated with the same high frequency mode. So high frequency components aren't dealt with very well using the coarse grid correction, right? They tend to get amplified. So we have to hope then that whenever we do our smoothing step, we can take care of those errors. All right, so now I said last time that an exercise to show that if I take the Euclidean 1 norm or the Euclidean norm on the level 1 grid of this vector, then I get this object. And so what I want to do now is take a little break and show you how I get this. So I wrote some notes on this. Now, I'm going to do a related calculation for this, which still works. And I'm going to do the related calculation that was associated in chapter 3. So in this case, I have a little bit more going on here because E1 is, and somebody has their, I think somebody has their microphone on. So if you could mute, that would be helpful. Thank you.
Sorry, it's me.
Oh, well. We're all good now. Okay. All right. So this guy is I1 minus pi1 tilde. And I'm adding a little bit extra here because it was, I think, K1 to the M1. So that looks like an R, so let me correct that. All right, so the calculation that I'm about to do, I really only want this term here, but if I just set M1 to be equal to 0, then it's going to return the same calculation. So this is a calculation we actually did or wanted to do in chapter 3. So let me go through the gory details of it. All right. So we'll only do this once. I'll show you how how kind of horrific it is, and then we won't do it. We won't bother to do this again. All right, so the a similar sort of scenario unfolds whenever we multiply this E matrix times a mode from either uh, the high frequency range or the low frequency range. So let's start with the low frequency range. And what we get is alpha k times v1k plus v1k prime. So this is exactly the same as what I just showed you. The only difference is this was just sk, and now this alpha k can be whatever we want, right? So I think in this case it's sk times the eigenvalues associated with this guy. And the same with the second one. Okay, so E1 V1K prime, that's just going to return BK. So you can think this is just going to be CK roughly. If we just have this part, then it's just going to be CK. V1K, V1K prime. So those are my two modes that get returned. So this holds for the high frequency or the low frequency range. And this is high frequency range. This is low frequency counting, but notice I'm using K prime here. All right, so I want to show a similar sort of calculation, and effectively this is the calculation, or essentially this is the calculation that we wanted from chapter 3 for the very last proof. So I'm going to expand the error vector in the basis of eigenvectors for the stiffness matrix. So in the last calculation, we were doing V1 here and expanding that. And so whether it's V1 or E1, it doesn't matter. All right, so I'm going to expand that in this basis. Now, I can do this in a couple of different ways. I could write this as, and I think that's what I want to do, sum k equals 1 to n0 plus 1, delta k, E1k, V1k, plus E1k prime, and V1k prime. And the reason why I can do this is because I'm just counting differently. All right. So I'm in this counting, I'm doing the low frequency all the way up to the high frequency. Okay. And I'm counting them separately. In this counting, I'm counting only up to the middle point. So I'm counting in the K equals in the low frequency range, but I'm counting both modes together all at once. So I'm counting K and K prime modes. So this means low frequency and then it's high frequency relative. And now the only difference is, or the only thing I have to take care of is I have a double counting whenever K is equal to N0 plus 1. And in that case, remember K and K prime, whenever K is equal to N0 plus 1, are the same. And so all that I'm doing is counting this guy twice whenever K is equal to N0 plus 1. And so the delta is introduced so that I divide that one by a half. That's all I'm doing. Now, considering that I can write that vector in this way, in this interesting way of counting, now when I multiply E1 times that vector, here's what I get. So if I write it in the usual way, then E1 just comes in and attacks this mode by itself. Okay, so that's sort of the standard way. But if I write it in this second way, then the E1 comes through the sum and it attacks this guy and this guy separately. So that's what I get there. Now, all I'm going to do is I'm going to use the fact that I have these guys tabulated in this interesting way of counting, okay, that I'm using now. And I'm going to substitute in these two formulas from above. All right, so again, and delta k is equal to 1 whenever k is not equal to n0 plus 1, and it's equal to a half whenever k is n0 plus 1 to take care of that double counting. And by the way, this this calculation solves essentially almost 3 homework problems all at once because 3 of the problems I asked you to do were more or less exactly the same as this. All right, now again, we go up to above and we replace E1 V1K with this vector and E1, forgot to put my 1 here, V1K prime with this vector. And so that's what I get here, right? Those are those 2 replacements. And now what I want to do is I just recognize that this can be, forgot my close bracket here. You can do this in one of 2 ways. I could think about pairing these guys together, right? And finding the coefficients of that, and then also finding the coefficients of these guys and sending them off separately. But I noticed that actually the coefficients for both sums are the same. And so I can write using the distributive property that all this complicated mess is equal to this. And I'm going to define this thing in here to be gamma k. So again, this going from this step to this step is just distributive property where I pull out this common factor. All right, next. Well, next I'm just writing this as gamma k, simplifying things a bit. And now I want to calculate the 1 norm squared of that vector that I just computed here. So this is sort of bookkeeping, and now I want to throw this into the 1 norm. Actually, this is the Euclidean norm on level 1, and I want to square that. So that's the Euclidean inner product of this with this, okay, vector with itself. But now, when I do this computation, I'm going to number this by k equals 1 to n 0 plus 1. I'm going to use a separate index, a different index for the second sum. I'm going to use m for that so that I don't mess up the indices. Otherwise, they're just the same things. All right, so let's use the linearity property of the Euclidean inner product on the level 1. So linearity means that all of these sums can come out, okay? So I just bring the sums plus any coefficients out. And then I just have this inner product with this, and then you just FOIL it. So then this inner product with that, this inner product with that, and finally this inner product with that. Now I'm going to use a fact that I know what the inner product of any vector is with a relative in that same basis. So V1K and V1, let's use M. That's equal to N1 plus 1 over 2 times the Kronecker delta dk delta km. All right, so it's 0 because they're orthogonal to each other, except when k and m are equal, and then when k and m are equal, I get the normalization constant. And it's the normalization constant is nicely comes out to be n1 plus 1 over 2. So I just did 2 steps here. So I brought that normalization constant out, and then I put all of my Kronecker delta symbols inside these parentheses here. So I get 4 Kronecker deltas. For example, this guy here, when I multiply with that, that gives me a K prime M Kronecker delta, and that's that guy. And when I do this one and this one, that gives me a K M prime, that's that one. Okay, so those are the 4 Kronecker delta symbols I get by doing that multiplication. Now I make a realization. I'm counting in the low frequency range, so let's write this out. So it makes life easy if I just do K, K prime, M, M prime. And I do 1, 2, I'm just going to do the example where N1 is equal to 7. And so I have 7, 6, 5, 4, 3, 2, and 1. And then I have, of course, M goes the same. 2, 3, 4, 5, 6, 7. and 7, 6, 5, 4, 3, 2, and 1. Okay, so those are my two lists of numbers. And I have to think about when can K and M prime, well, let's do this one first. When can K and M be equal to each other when K and M are in this low frequency range? So 1 to n0 plus 1, 1 to n0 plus 1. Well, in a bunch of places, right? They could be equal to each other there at 2. They could both be 3, and they could both be 4, right? So a bunch of places for that guy. But what about K and M prime? Well, K gets counted down from the top, and M prime is going to go from the bottom. The only place, right? Actually, I messed that up. K gets counted this way, and M prime is going to be counted this way, right? Because we're counting M1 to N0 plus 1, so that's this range, right? But M prime is just going to be 7, 6, 5, and 4. K is going to be 1 up to 4. The only places they can equal is whenever K and M prime are both equal to N0 plus 1. The same is true for this one. This is a typo here. That should be no prime on that one. So I had a prime there. The prime shouldn't be there. K prime and M. Well, remember I'm counting K from 1 to N0 plus 1. So K prime in that case is going to be 7 down to 4. And M is going to be 1 up to 4. The only place they can equal is whenever K prime and M are equal to 4, or in general, whenever they're equal to N0 plus 1. So I'll take care of those two momentarily. What about K prime and M prime? Well, those guys are, so K prime is going to be in this range. Oh, let me do it like this. K prime is here, M prime is here. Well, those are going to be equal precisely whenever K and M are equal to each other. So I can actually take this guy and say, I can use the fact that K prime, M prime is equal to delta Km. All right. So now I'm going to do my replacements. Now remember what happens when you have a Kronecker delta and two sums. One of the sums disappears. So for example, in this guy, I have two sums, the sum over K and M, and this is going to collapse. And the only thing that's going to survive is whenever K is equal to M, and then I just have one sum. So whenever K and M are equal, this is equal, and these are equal, and I just get delta K squared, delta or gamma K squared, right? And I simply have one sum. All right, so that takes care of this first term here. And I'm going to pull this guy out. That normalization goes all the way out. What about this one? We said that that's only equal whenever K and M prime are both equal to N0 plus 1. So whenever K and M prime are both equal to 0, N0 plus 1, this is going to be, both of these are going to be equal to a half, so that becomes a fourth when I multiply those together. And these guys combine together to give gamma N0 plus 1 squared. The same thing happens for this guy. Now this one I said this delta, this Kronecker delta can be replaced by K equals M or delta Km. And so for that one, I'm just going to collapse the sum to become sum K equals 1 to N0 plus 1 delta K squared gamma K squared. Okay, so whenever K and M are equal, K and M are equal, those become squares. So all that complicated mess reduces down to this. Now, this is a bit weird because I want to have a result in the end which just is delta K, not delta K squared. So let's see how can we get that. Well, first of all, notice that now this sum and this sum are exactly the same, so I can combine those two to get 2 times the sum. And these guys are both the same, so I can combine those to get 2 times the sum. All right, so now all I have to do is figure what happens whenever, for this guy, whenever K is equal to N0 plus 1. Well, I get delta K squared, that's going to be delta n0 plus 1 squared. So that's going to be a fourth, right? Let's pull this 2 and this 2 out. Okay, so that'll cancel that guy. But I get a fourth here and a fourth here. They add together to give a half. That returns me back to the old original delta k, because I have a quarter plus a quarter gives a half. Okay, so I'm just using the fact that I have 2 times delta k squared equals, well, I should say n0 plus 1 is equal to delta n0 plus 1. Any other time, it's just equal to 1, so it doesn't matter. So that's why I can return this back from delta k squared to delta k. So this proves the result that I wanted. Okay, if you look back at the thing that we were trying to prove, this is exactly it. All right, so let me go back then, and I'll show you that that's more or less what we were after. So I wanted to show that whenever I take the Euclidean norm of something which looks like this, I'm going to pop these guys in there. I use the expansions that I had here. I called this guy alpha k and this guy beta k, but we can now change him back to sk and ck. And I just get n1 plus 1 quantity, sum k equals 1 to n0 plus 1, delta k gamma k squared. All right, so it's exactly what we wanted to show. Previously, I think we argued that maybe this was alpha k and beta k, so it's quite generic. So we can change it back to sk and ck. But that's the technique. That's the basic technique for doing this. You just have to be careful about keeping track of your indices, realizing that when I sum over the low frequency range, then there's only one case where high frequency numbers and low frequency numbers can be equal to each other, and that's whenever, for example, um, the only way a k prime and an m could be equal to each other is whenever both are equal to n0 plus 1. So this calculation involves something a bit different. This calculation involves the energy norm, so it involves the A1 matrix, the stiffness matrix. But I can rewrite this exactly in the same fashion as I had up above. I can rewrite this as a Euclidean inner product where I have A1 to the 1/2 power. Remember, because I'm writing this guy as its energy inner product, but I write this A1 and I bring it in here and change this to a Euclidean inner product. And then I separate A1 into its two parts. Remember, we said that any SPD matrix can be written as its square root times its square root. So that's what I'm doing. I introduce this guy in here, split it into its square roots. Then I move one of those square roots over to the other side, and I get this line. But now notice that this is just the same thing, same vector appearing in both locations. So what I do is I play the same trick as I did up here, or with the proof of that, proof of this guy. I try to write this. I try to write some expression like this, but now I'm going to put A1 to the 1/2 power here. A1 1/2 power. Well, what happens whenever I write A1 1/2 power times this vector? Well, it's going to produce the same set of vectors that I get here, but now I'm going to liberate an eigenvalue and another eigenvalue. So I liberate an eigenvalue associated with the frequency or the wave number k, and also one associated to wave number k prime. But now these eigenvalues are not going to be lambda 1, they're going to be square root of lambda 1. And so that's the only difference. So it is a complicated piece of calculation, but now that I showed you in that other set of notes how to do it, I think you can accomplish it, figure it out. The interesting thing here is I get more or less exactly the same thing as I got previously. Now I'm computing in this energy norm. Previously, I got n1 plus 1, the sum delta k gamma k squared for this norm. Well, notice I get the same thing back, but plus this extra bit of business. Now, let's think about this, lambda 1k and lambda 1k prime. I said that if I take the average of those two things, you precisely get this number out in front. We can show this by a picture, actually. So if I take and plot lambda 1k as a function of k, remember it looks like that. And lambda 1k prime, if I plot that guy, it's the mirror image. And they're exactly the same here in the middle, n0 plus 1. Well, the upper limit for these guys are 4 over h1. All right, so let's average these two together. It doesn't take a lot of work to show that, well, when I average this point and this point, I just get 4 over h1. And when I average these points, I get 4 over h1. And let's see, why am I, oh, no, I need to average. So when I average, I need to divide this by 2, right? So I'm going to get 2 over h1 when I compute the average. So the average is just right here through the middle. So that's sort of a picture approach to why, and again, this here is going to be lambda 1k, and this guy is lambda 1k prime. It's a pictorial approach or proof that this guy, when I average it, gives me this number here exactly, 2 over h1. Well, that's good because I said in this estimate, actually it's an identity that I want to prove here, that I get something involving this lambda, capital lambda 1, which is my upper limit for all of the eigenvalues. So I can write that as, and you can see that this guy is going to be 4 over h1, so 2 over h1 is just 1/2 of that value. Now to get the result that I actually wanted, I'm just going to move this guy to the other side, take square roots to get rid of the squares, and I get the result. So let me show you again what that was.
Question.
Question, yeah.
Yeah, I think you go back to the drawing you draw. I
That
think
one?
I think I think I have a nicer argument because we know SK. I mean, like lambda one and lambda one k prime, they're just sine square and cosine square, so they add up
Yeah,
to one. And then one, but you multiply 4 by h1, so it's 4 divided by h1 for the numerator, and then you divide it by 2. You just use the sine square plus cosine square equals to 1.
exactly. Yeah, yeah.
Yeah.
That's right. That's another way of looking at it. Then this curve is going to be a sine curve and sine
Sine square
squared,
curve.
and
Yeah.
this one will be a cosine squared. Exactly.
Yeah.
And it's also the same picture that I pointed out earlier, or similar, right? It's the same reason why these guys agree in the middle. Of course, they don't have any prefactor here, but these guys will have that prefactor so that we end up with 4 over h1. But in any case, it's the same sort of reasoning. Sine squared plus cosine squared is equal to 1. Yeah, perfectly so. Yeah, any other questions about this? So, why are we interested in this? Well, this is just a kind of computational lemma, which is going to give us something more impressive in a moment. But for now, this is kind of a key and fundamental result that we can derive for our two-grid algorithm. And the reason is, well, it's not really the full two-grid algorithm. Notice that it's only for the coarse grid correction error part. And it's saying that the Euclidean norm is related to the energy norm through this coefficient. This coefficient is going to be important for us in a little bit. I can't really explain or I I haven't really thought about a good explanation of why this is so or why this is important at the moment. but we're going to see where we use this in the next result. Now, in the general framework of multigrid, so notice we're working with finite element, we're working in 1D, and we're working with a uniform mesh. So the uniform mesh allows us to use Fourier analysis. That's the main reason for using the uniform mesh. It allows us to use a very simple Fourier analysis. Now, in the general finite element framework, when we're working in 2 dimensions and 3 dimensions and for any dimensions we want, really, we won't be able to show a simple estimate like that, but we'll be able to show something similar. We'll be able to show something like this, that the one norm or the Euclidean norm of that vector is related to the energy norm, the same vector. We can't show equality, but we're going to be able to show it with a constant, some constant which is independent of h, times the square root of 1 over the spectral radius. So remember this guy, I'm going to call it the spectral radius. It's not exactly the spectral radius. So 4 over h1. It's an asymptotically sharp estimate for the spectral radius. So it's greater than the spectral radius of A1. Remember, that is equal to the largest eigenvalue. And the largest eigenvalue is given by N1. Okay, and so this estimate here is perfectly good, perfectly reasonable, but there's a little bit of a gap between this number and this number, but it gets sharper and sharper, or closer. The two numbers get closer and closer together as h1 gets smaller. So the gap gets closed essentially. So we call that an asymptotically sharp estimate. So this lambda 1 capital lambda 1 is not equal to the spectral radius, but it effectively is. It's almost the spectral radius. It's asymptotically sharp estimate for the spectral radius. So that's what appears here in the square root. And this is what we can show in the general finite element framework. We're going to do this in chapter 6. This estimate will come back. So whereas now we're able to establish this with equality, and I think C1 is equal to the square root of 2. Later on, we're only going to be able to do this with an inequality. But this is just to show you how things work out very nicely in the uniform mesh case. All right, this is the estimate that we're actually after. And I'll be able to motivate why this estimate is useful once we get to the convergence proof. You'll see it very clearly there. For now, what it's saying is this guy here is an energy norm, right? And this is what we sometimes call the double energy norm or the squared energy norm. All right, so if you know a little bit about Sobolev spaces, then you'll know that this A1 represents the H1 Sobolev norm, and this A12, this represents the H2 Sobolev norm. So if you know about Sobolev norms, H1 is associated with that guy, and H2 is associated with the square. And if you think about it, it kind of makes sense. A1 kind of will represent the gradient. This will represent a gradient squared, which is like the Laplacian. So that's why you get this correspondence. And we're going to get into all of this, where this comes from and how this relates to Sobolev spaces when we get into chapter 6 and we talk about the finite element method. So we're going to come right back to this guy, and we'll explain it in detail, why it's important later, how it relates to Sobolev norms and Sobolev inequalities. Right now, I don't really have a good way of explaining what it is. I'm just going to demonstrate it and sort of let you take it at face value. So the estimate I'm trying to show is that when I measure the error in the energy norm, it's less than a constant C1 times that constant we just saw on the last estimate, the last identity, the square root of the spectral radius. Again, I'm going to call this the spectral radius even though it's not exactly equal to the spectral radius, times this heavier norm of V1. So we lose this guy, okay? We lose this guy, and we're just going to get the norm of V1, but it's going to be it's going to be with a different weight, okay, or a different scale. All right, so let's prove this. And again, I'm not really doing a good job of arguing why this is important right now. I'm going to hopefully hold off on that in a little bit. I do want to point out this result, once you get it, is what's called an approximation property. If you can establish this for some constant, an approximation property. So let's start off with the energy norm of that error matrix times an arbitrary vector v1, and we'll square it, of course. So if we do that, that is going to be the same as the A1 inner product of this vector with itself, but I'm going to skip that step and write it directly as a Euclidean inner product of a vector with this vector, but with the addition of this stiffness matrix coming over on the side. Now, it doesn't matter where I put this stiffness matrix. I could put it here or here, and the reason is because it's symmetric in the Euclidean inner product. So symmetry in the Euclidean inner product means it can hop back and forth in these two locations. Doesn't matter. All right, now the next step is, as I said, we're going to move that guy over to the other side because we can. Move it over to the right-hand side, and it goes over without a transpose because it's symmetric. Now we're going to take this part here, multiply it out. So it's going to give us two terms, A1 times V1 and A1 pi 1 tilde V1. And then I'm going to use the linearity of the second component of the Euclidean inner product. Remember, that gives us two vectors. So I'm going to split that into the inner product of this vector with that first vector minus the inner product of the first vector with the second one. All right, or I should call this vector the one on the left. The left with the first, and then we're going to do the left with the second. So that's what produces these two terms. Now, I want to show that this guy here is actually equal to 0. All right, now what assumptions do we make in order to get that? We need to make the assumption that A0 satisfies the Galerkin condition, or in other words, that A0 is equal to the wrap. Right, so Galerkin condition means that A0 equals R0, A1, P0, the wrap condition. Well, we showed that if that holds, then the pi 1 tilde matrix, we showed this in a previous chapter, then the pi 1 tilde matrix was equal to a projection matrix. In other words, it has the property of a projection matrix that if I multiply it times itself, I get the original matrix back. So we're going to use that. So we're going to use the fact that if the Galerkin condition is satisfied, then we know that this holds. So that's precisely where we're using the Galerkin condition. Okay, so we're going to show that this guy is equal to 0. So let's write it. I wrote it in a different way here. This is the thing I'm actually working with. But notice that that's just, if I bring this A1 down, that's just the A1 inner product of this with that. Okay, but this is actually the thing that I was working with on the right-hand side. That's the second vector or the second inner product that I want to show is equal to 0. So let's write out what is the definition of this pi 1 tilde matrix. Well, pi 1 tilde is exactly equal to P0, A0 inverse, R0, according to our prescription, our definition in chapter 2. And by the way, I just noticed I have a typo here. So that guy has that A matrix should be, I'll write in some code that you guys won't understand. So that's, I used the wrong formatting on that A matrix. But in any case, the pi 1 tilde is P0, A0 inverse, R0 times A1. Now I'm going to multiply, I'm going to use the associative property and just grab this guy and leave this guy to hug onto V1, all right? So I just used associative property to reassociate this multiplication. Now I'm going to take this whole product, remember I'm operating in the Euclidean inner product, and I'm going to move it back to the other side. Well, it moves back to the other side with a transpose, right? But now let's untranspose this guy. Well, if we untranspose, that just becomes R0 transpose times A0 inverse transpose times P0 transpose times A1 transpose. But now we keep in mind that R0 is equal to P0 transpose. And similarly with P0, P0 transpose is equal to R0. The stiffness matrices involved here are both symmetric positive definite, so they don't change. And so what I find is that this whole thing just becomes the pi1 tilde matrix back. Okay, so in other words, I just get that vector over, or that matrix over there. So I get pi1 tilde times 1 minus pi1 tilde. All right. Over here, I have A1 V1, but I can pull the A1 down in a definition, right? So instead of writing this as the Euclidean inner product, I'm going to rewrite it as an energy inner product by bringing the A1 out. But the point is, whether I do that or not, doesn't matter. This matrix here is equal to 0, right? Because pi1 tilde times I1 minus pi1 tilde, that's equal to pi1 minus pi1 tilde squared. And remember, this is a projection matrix, so we showed that that equals pi1 tilde, and that's because the Glerkin condition holds. And so we just get the same matrix minus itself, and we get 0. So this is 0, identically that matrix, and so obviously the inner product works out to be 0. So when I did this manipulation, I just showed now that this is equal to 0, and I only have that. So that's where I'm going to start now. Okay, I'm going to drop that second term. It's gone. I have that, and I'm going to apply the Cauchy-Schwarz inequality. So I hope you remember Cauchy-Schwarz. Cauchy-Schwarz says that if I have any vector, VW, in the Euclidean inner product, and this could be any inner product, but I get the V norm times the W norm. Okay, both in the Euclidean norm sense. So this is Cauchy-Schwarz, right? I'm applying it to this one inner product. If I apply it to the A1 inner product, then I have to use the A1 norms on both sides. So I get the Euclidean norm of that first vector and the Euclidean norm of the second vector. I'm going to keep this guy, and I'm going to use the identity that I proved in equation 4 right here. Let's see. Blah, blah, blah. So I use 4. I'm just going to plop in that. I'm going to use the identity I have for this. But before I do that, I recognize that this guy here, I said in the preliminary steps of this chapter, I didn't review those again today, but I did this in the last lecture. I showed that, well, this guy, if it appears against this vector, it comes out as this heavier norm, this this double energy norm, A1 squared. And this is the norm which I said is like the Sobolev or the 2 Sobolev norm or the H2 Sobolev norm. So we're going to get to why that is so once we talk about the finite element method. For now, we just going to have to put that in our pocket. And then we're going to use the estimate that I had in 4 to replace that. That's the Euclidean norm with this energy norm. But now notice that I have an energy norm on this side squared and the energy norm on this side without the square. And I can use cancellation property as long as this is not equal to 0. And I'm going to assume it's not equal to 0 because if it was, then the estimate that I want to prove is trivial anyway. If it's not equal to 0, I can cancel this term, and then I get the estimate that I wanted to show in the first place. So that's the result. So let me go back. Let's see. So we have it. Yeah. I'm going to go back and just emphasize that this is the structure of what we're going to call an approximation property, an approximation or the approximation property. What we're usually interested in is figuring out what is the size of this C1, this coefficient, in this inequality. Well, here, because we're doing a very basic Fourier analysis, we can show that that constant just works out to be square root of 2. All right, so that's what we proved. Now, this corollary that I'm stating here is just that part that we're going to use this over and over again. And if the Galerkin condition holds, then we showed that this inner product was equal to 0. So if I expand this guy out, I get two terms. I get this plus that, but this one is equal to 0. So this is equivalent. So two equivalent statements. For all V1, this equals that is equivalent to saying that this inner product is equal to 0. So we already proved that. That was part of that was essentially this slide here. So I'm just tabulating that because this corollary is going to be useful for us later. And it rested upon the fact that A0 satisfies the Galerkin condition. Again, estimate 6, the one we proved in the previous theorem, is what we call an approximation property. Here, we can show that the constant C1 is equal to square root of 2. But in general, whenever we're working on this in the finite element setting, and we're going to be using some very complicated frameworks where the mesh could be very complicated, etc. We might not be able to show that we might not be able to figure out what the constant is or what the size of it is. But if we can establish it with some constant, which is independent of all the other parameters involved in the multigrid method, then we could call that estimate an approximation property. And again, we're going to come back to why that is called that when we talk about this in the finite element chapter, and that chapter is chapter 6. All right, so we just completed this estimate, which we called the approximation property. So now we're going to get into the smoothing property. But before we do that, I'm going to switch smoothers a little bit on you from chapter 3, but not in an essential way. I'm going to shift kind of the details of the smoother, but not the essence of it. So remember in the last chapter, we were harping on this thing called the damp Jacobi smoother and why it was so useful and helpful. But now we're going to switch this smoother out and use instead the Richardson's method. But it turns out in this case, for this very simple setting, these smoothers are really pretty much the same thing. That is, damp Jacobi or weighted Jacobi and the Richardson's method are more or less the same. In fact, the smoother that I'm going to introduce now, called the Richardson smoother, is just going to be equal to the damp Jacobi smoother, but instead of taking omega equals omega naught, which was 2/3 our optimal omega, if we set omega equals to a half, we get this smoother right here. So the Richardson smoother that I want to use, remember how Richardson worked. Richardson was, for the error transfer matrix, it worked out to be, and I can pose it in this equivalent way without loss of generality. We can just talk directly about what the error transfer matrix looks like. It was I minus, I think it was 1 over omega times the stiffness matrix A. So that's how that's what we found was this the error transfer matrix for the Richardson smoother. Here we're going to choose this omega to be exactly equal to our asymptotic spectral radius. Okay, so the capital lambda 1, which is 4 over h1. Now recall that the eigenvalues for our stiffness matrix, we had a nice formula for that. And let me explain this guy again. Our eigenvalues, if we plot them, it just looks something like this, right? And if you learn nothing else from this course, I think you're going to learn the eigenvalues for the stiffness matrix. You'll never forget them. They're so I plotted things here as if k was a continuous variable. It's not. It's a discrete variable. So the The eigenvalues are actually discrete numbers along this curve, right? But the good news is we know that they're all positive. A1 is clearly a symmetric matrix. Now we know that all the eigenvalues are positive, and we have a nice upper bound for that, 4 over H1. Now remember I said that that's not equal to the spectral radius, but it's an asymptotically sharp approximation of the spectral radius. Okay. So this Richardson smoother somehow involves, instead of using, remember we had some formula for the optimal omega whenever we were talking about the Richardson smoother. Well, that was optimal um, if we wanted to make our error reduction as small as we could possibly make it across the whole spectrum. Now we're going to use this as a smoother, and so we won't be interested so much in minimizing that error reduction factor across the whole spectrum. We're going to want to prioritize the error reduction of high frequency modes. So that's the idea. So I'm going to explain why we're choosing this guy and why it's not necessarily optimal in the classical sense, but it's going to be optimal for our multigrid sense. Now, also recall for our damped Jacobi method, remember for that one, we had that free parameter called omega that if we choose that, that sets up how we're doing damping, and that sets up the exact description of the damped Jacobi method. So in that case, our error transfer matrix worked out to be I1 minus omega times H1 over 2 times A1. And so now we recognize that, well, if we choose omega equals to a half, I'll have to go back and check. Yeah, I think this is correct. This is a different omega than I was talking about over here. Remember we had a different omega associated with Richardson smoother. This omega is our damping parameter. In any case, if we choose this to be equal to a half, then this works out to the same smoother that we have right here because the error transfer matrices are the same. Okay, so just choose omega equals to 1/2. That means that the damped Jacobi method with omega equals a half is just exactly equal to the Richardson smoother. In fact, we worked out all the details for this. We worked out what are the eigenvalues of the error transfer matrix, and so now we know that the eigenvalues for that error transfer matrix for Richardson is just going to be the eigenvalues that we previously computed and tabulated as these mu eigenvalues, but we choose omega equals to a half. And if we do that, then we find out this nice little formula here, which is something else we're going to keep in our pocket. See if I can make a nice square box here. Rectangular. There we go. All right. So we can show that those eigenvalues for the error transfer matrix are the same as the eigenvalues for the damped Jacobi method, but choosing the weighting parameter omega equals a half are just going to be 1 minus lambda 1k over our asymptotic spectral radius lambda 1. Okay, so that's just a very simple simple argument. And now what we could furthermore show, and this follows from a picture, I think we have that on the next page, that all of the high frequency values of all of the high frequency eigenvalues are less than a half in size. So let me show you why this is true. Well, this is kind of proof by a picture. If you look at those eigenvalues for the damped Jacobi smoother, aka the Richardson smoother, but whenever mu is equal to a half, then the curve looks something like this. And keep in mind, I'm plotting this as if k was a continuous variable. It's not a continuous variable, and so the eigenvalues are these discrete points along here somewhere. The smallest eigenvalue is like somewhere up in here, so it's very close to 0. But the good news is what we're showing now is these eigenvalues from n0 plus 1 up to n1, they're all eigenvalues which are less than a half and greater than 0 um, in absolute value. Well, in not absolute value, in actual values, but in absolute values, what's important here is that all of them are less than a half. Okay, so that's cool. previously we said, okay, so whenever we chose omega equals omega naught, that gave us values which looks something like that. We could show that the values were between plus a third and minus a third. We're not going to be so worried about that here. We're gonna be okay with having the values between 0 and a half. All right, so now next concept is the smoothing property. Now that we've changed the smoother, we have the approximation property. Now the smoothing property tries to quantify the error reduction associated with smoothing, but in these quote unquote Sobolev or energy norms. Okay, so the next thing we want to prove is this so-called smoothing property in these so-called um, energy norms or Sobolev type norms. Before we get there, and probably the last thing that we can do today is we have to establish a technical lemma. And this one is, as with most technical lemmas, they're not really instructive until you actually use them and figure out what the heck's going on. So this technical lemma says something about a function. Suppose that m is any natural number. Then for this function, x times the quantity 1 minus x to the 2m power. If I take the maximum of that over the domain x between 0 and 1, then this function is less than 1 over 2 times m. So in other words, this function, and I probably should have looked and observed what this function looks like. I think it looks something like that between x equals 0 and 1. And all we're saying is its maximum, which can be obtained by finding using the derivative, is less than 1 over 2m. Okay, so this is what we want to show. So this is a technical lemma that we're going to use to prove a more general or more important result. Well, there are two things you have to do. So the first thing is you have to, let's define this function, this thing we drew over here. We're going to call that f of x. So what we have to show is that if we can find a extreme value in 0 to 1, then that has to be interpreted as a maximum. Well, how can we do that? Well, this is a fairly simple function. It's a polynomial function. All we would have to do is show that the curvature or the second derivative here is negative. And that's fairly easy to do. And I'm going to leave that up to you as an exercise to show that the second derivative of f in this domain is negative. The other thing we can observe that is that f at 0 and 1 is equal to 0. That's fairly simple to see. And of course, that's what I've plotted here. And otherwise, f is a positive function on that interval. Okay, I probably should have added here that f double prime from x is less than 0 on 0, 1. Something you can check. So now if all those things hold, then we can just simply take the derivative, set that equal to 0. And if you do that, then you come up with an extremal point that is x0 equals 1 over 2m plus 1. And now to find out the extremal value of f, all we have to do is plug that number back into the function. So let's plug this into f. And if we do that, we know that the extreme value is equal to this complicated number. Now, what we're going to focus in on is this guy right here. This guy right here. Let's start with that. 2m over 2m plus 1. What do we know about such a number? Well, let's think about this. This could be something like 8 over 9. That's a fraction, right? And that fraction is less than 1. Well, if we have a fraction which is less than 1 raised to a positive power, the whole thing is less than 1. So we can replace this part by 1, okay? And we can get something bigger. What about the second thing? Well, this one is obvious because 2m plus 1 is bigger than 2m, and so the reciprocals follow the reciprocal chain of inequalities. 1 over 2m plus 1 is clearly less than 1 over 2m. Again, because 2m plus 1 is greater than or equal to 2m. And so that's the result that we wanted to prove. The result follows. So I only have time now to state the smoothing property. We don't have time to prove it, although the proof is actually a lot easier than the proof of the approximation property. So let's suppose that we're on a uniform and nested two-level grid. Suppose that A0 satisfies the Galerkin condition, although I may need to come back and check. I don't think I actually need this. So let me put a question mark beside that. Do I need that? Because when I reviewed the proof before class, I don't remember actually using that fact. Okay. So if we use our Richardson smoother on our problem, equivalently, that's the damp Jacobi method with omega equals to half. We know that now. Then we can show that K1 to the M1 power. So this is the error transfer matrix for our Richardson smoother raised to the M1 power. The reason why we're raising it to the M1 power is because we know in our two-grid method, we're going to do M1 applications of smoothing. We're going to apply that matrix to an arbitrary vector, and we're going to measure its size in this double energy norm. Okay, this is like the H2 Sobolev norm, which I'll show you in chapter 6. So this heavier norm of this error transfer matrix. So what we can show is that the error associated with this matrix is essentially something like a constant, again involving this this asymptotic spectral radius, lambda 1, over m1. Okay, so this parameter translates into here. But instead of having V1 in the double energy norm, we're measuring V1 in a lighter norm, the just plain energy norm. Okay, so it's going to be clear when we do this proof why this guy transfers from this double energy norm to this single energy norm, or in other words, this order 2 Sobolev norm to this order 1 Sobolev norm. Now, when I talk about Sobolev norms, that won't be clear until chapter 6, but that's effectively what is happening here. So I'm going to come back and prove this. This is where we'll start next time. And I've already gone a minute over, so I apologize for taking that extra minute of your time. We'll stop here and I'll take any questions that you guys have.